If you've spent any time on watching other math YouTubers, you've come across someone showing how 0.9 repeating is 1. In particular, you can produce the following little stint of algebra to prove that this is the case just using some multiplication and subtraction to show that the x here is 1. There's another way to think about this, though, as it relates to fractal geometry and one of the mathematical devices used to generate fractals, iterated function systems. To start, an iterated function system is a finite set of contraction mappings on a complete metric space. Now, we're not going to focus too much on what complete means here, but just know that a metric space is a set with a notion of a distance. And we're going to require that it operates in a similar way to how we most often think of measuring the distance between 2 points in the plane. That is, a metric here will have similar properties to the Euclidean metric on the real numbers. A contractive mapping, however, is just a function from a metric space to itself, such that the distance between two images, f of x and f of y, is less than or equal to the distance between the two pre-images, x and y, up to a constant multiple L, where L is strictly less than 1 but greater than or equal to 0. For example, if we take this equilateral triangle, or roughly sketched equilateral triangle with the Euclidean metric as our metric space, we can have 3 contractive mappings, each that contract the triangle by a factor of 1/2, and where each of the 3 triangles produced is on the interior of the original triangle, and each has one vertex on the vertices of the original triangle. That was a mouthful, so it is right here, shown in picture form right there, and the functions that actually make this happen are listed over here as well. Now, there is a ton of really cool stuff surrounding iterated function systems, but we'll focus on 2 of them. One, they are a tool that is used to produce fractals, which quite honestly is a terrible math word. Doesn't really have a great definition, but for our purposes, a fractal is a self-similar thing, or has self-similar geometric properties. And we are going to get this behavior by taking our iterated function system and iterating it on some set, as the name would suggest. The iterated function system here, from our past example, actually generates Sierpinski's triangle. The other cool thing is that even though points in a self-similar set are really hard to keep track of most of the time, we can use the iterated function system to keep track of what points are actually present. So, for example, if we want to know what happens to the triangle after applying the first and then the second and then the third functions in our iterated function system, we could represent it by the decimal 0.123, as we did the first function and then the second function and then the third one. And we would end up with just this small triangle, having started with the big one. So somehow, after all of that weird geometry stuff, we got back to decimals. It may seem a little bit odd, but decimals from 0 to 1 can actually be thought of as the result of applying an iterated function system repeatedly to the interval from 0 to 1. In this case, we will have 10 functions in our system instead of 3 in the system that produced Sierpinski's triangle. This should make just a little bit of sense, even if you aren't convinced that the line segment is a fractal. So when you zoom in on a line segment, you get another line segment. In that sense, it is self-similar. And so it's presenting a lot of similar behavior to that of Sierpinski's triangle. Now, thinking about what these functions do, notice that if you apply each function to the interval and then take the union of those images, you just get the interval again. So 1 is still hanging out after one iteration, but when we look at what those image intervals are symbolically, we only have the decimals 0.0, 0.1, 0.2, 0.3, and so forth, all the way up to 0.9. And 1 is in the set that corresponds to the decimal 0.9. After more iterations, you should end up with 1 in the set corresponding to those decimals with all 9s in the expansion. After infinitely many iterations, we're only going to be left with 1. And so 0.9 repeating from this fractal geometry lens is just the set containing 1. Now, this might seem a bit odd, but we actually identify points with this expansion all the time. That is, given a point in the interval from 0 to 1, we can find the decimal that tells us what functions from this iterated function system we needed to use to get to that point. So for example, let's say we have the square root of 2 over 2. Now if we plug that into a calculator, it'll spit out the decimal expansion 0.70710678118 and so forth. And so we would apply the 7th function from our iterated function system first, and then the 0th function, and then the 7th function, and then the 1st function, and then the 0th function, and then the 6th function, and so forth, to end up at the position of the square root of 2 over 2. It's similar when we were looking at 1. We know it is in the image of the 9th function after each iteration, so 0.9 repeating will eventually get us to the position of 1. Now, this approach to 0.9 repeating equals 1 is a lot more convoluted than just x is equal to 0.9 repeating, do some algebra, get x equals 1, right? So the reason that this is valuable is that there are more generalizations or more places you can go with this method of thinking than you can with the algebra sense of 0.9 repeating as 1. The first is a generalization of base. And the second is a geometric generalization. We won't get into all the details here. They are both definitely hanging out on the list of possible topics for future videos though. So if you're interested about a bit more detail behind these things, let me know in the comments below. Okay, so first off, decimal is a bit of a suggestive word because it implies that we must always continually subdivide whatever we're working with into 10 parts, in this case, the interval. And that is portrayed by the iterated function system since there are exactly 10 functions used. However, if we change the iterated function system in use, we get a different type of expansion of numbers between 0 and 1. So let's say we break up the interval with an iterated function system of 2 functions. Then instead of a decimal expansion of numbers between 0 and 1, we have a binary expansion of the numbers between 0 and 1. So if we go back to the square root of 2 over 2, instead of having 0.707 as the first 3 terms, we would have 0.101 as the first 3 terms in the binary decimal expansion. The way this generalizes 0.9 repeating equals 1 is in that of base. So 0.9 repeating equals 1 when we're talking about decimal expansions, but for binary expansions, we now have 0.1 repeating is 1. It's a little bit weird, but it works. Generally, if you have any base n expansion, then n-1 repeating is 1 in that expansion system. The second generalization is a little bit more geometric in flavor. Let's say that we're working with our decimal iterated function system, the one that produces decimals that we're used to, and we apply those functions to the unit square instead of the unit interval from 0 to 1. The addition in these functions is going to be a x-coordinate translation, and multiplication by 1/10 is just a scalar on both units of our plane x and y. After one iteration, instead of squares, we're going to have a rectangle that is 1 unit long and 1/10 units tall. And continuing this process, we'll eventually have no height left, and we'll end up back with the interval from 0 to 1, as we did before. The cool thing here is that 0.9 repeating still gets you to 1, in a sense, in this case, even though 1 here is the coordinate 1, 0. And it was independent of the set you started with. There are some caveats though, and since we're not getting into all the details, we're gonna leave that little black box of mathematical info for another time. But anyhow, that is all I have for you today. Hope you enjoyed this little journey into fractal geometry from the perspective of decimals. It's definitely a really interesting way to think about decimals. It boggles the brain a little bit if you're not used to it, but it's also really cool. I really enjoy it. So anyway, if you enjoyed this video, give it a thumbs up and subscribe for more mathematics videos. You can do so right here. And there is more stuff that I made over to the right here. As always, I am Nathan, this is Chalk, and I will see you next time.